Hey, good afternoon. Let's get started. So, if you are not here on Monday and you are interested in getting your paper, your exam, then just wait until the end of the lecture and you can come to the podium and I'll give you your paper. I posted the grades this morning. So if you haven't seen your grade, it should be available, or your score for the first exam should be available on Canvas now. So today we're going to start a new topic. On facilities design. And we're going to talk about space requirements. And this involves the design of different systems inside the facility and also outside the facility. So things like designing for a specific capacity in terms of your HVAC, for heating, for cooling the facility. Also things like areas that are needed for the employees. So how to design, for example, a parking space for your employees, which is part of the design of the facility. So today we're gonna start looking at some of those items. And the material that is discussed in this lecture is part of chapters 3 and 9 from your textbook. So this section or this lecture is connected to objective number 4, which is to be able to design layouts incorporating product, process, and personal requirements. So in this lecture, I split this lecture in 2 parts. So in this first part, we're gonna talk about the structural system performance, enclosure systems, and atmospheric systems. And then on Monday, we're going to look at the electrical and lighting system design and also life safety systems design. The objectives for the lecture is to provide an overview of how the system's elements impact the overall process of facilities planning, and also to provide an understanding of the different system elements within the facility. It's not to prepare the facilities planning to design a structure or seating, ventilation, and air conditioner or other systems. So basically that comment is trying to say is like, you're not going to be an expert in terms of designing an HVAC or heating system, but at least you will have enough knowledge to have a conversation with the person that is going to be in charge of preparing and developing that system in your facility. So you will still have an understanding at least at the capacity that you will need to cool your facility, and also to provide heating if you need that too as well. So the introduction. So as we have observed so far, we've been focusing on space design and the location of departments and how to look at the design from a manufacturing perspective. So the most difficult determination in facilities planning is the amount of space required in the facility. And there's some uncertainty that is inherited by the system. And those concerning the impact of technology, changing product mix, changing demand levels. So if you have multiple products, or if you are including new products into your facility, that would change that would include additional uncertainty in terms of your demand, and also in terms of how are you going to process those new products. Changing demand levels. So if you have seasonal type of demand in which you will see changes throughout the year, that also increases the uncertainty in terms of the impact of your design and the organizational design for the future. So one thing that we are experiencing right now is the impact of having a pandemic. So most of these large companies have seen a change in terms of work needs or workspace needs. They have observed that some people can work from home without issues, and they don't have to plan or they don't need to have a space for some of the personnel because they can work from home most of the time. So all these things add uncertainty into your system, and also uncertainty in terms of how are you going to design for your facility. The facilities planner then has the difficult task of projecting through space requirement for the uncertain future. Another thing that I have seen in the news a lot is companies that were located in these major cities that has a very high cost of living, and people working for that company now moving to other places where the cost of living is less, and how is that impacting the decisions that the company is making in terms of thinking about future expansion. Do they really need to live in that, or they really need to have a company space in New York City, for example, or in Austin, Texas? So as a planner, you have to look into those things. So if you're just going to have people sitting in a desk in front of a computer all the time, do you really need to have that space in a very expensive site? Or can you plan for a facility outside that area in which people can meet when they need to, but most of the time they will be working from outside or from home? So a lot of challenges, a lot of things. I think things are going to be different from now on. And we have to think about that when we are planning for the future expansion of certain facilities. Obviously, production, that's not something that you can do from home. You will still need a space to do manufacturing, to do warehousing, to do logistics. But if you are in the planning area or design area, so on, you might not need to have a space for that in your facility. Workstation specification. So we look at different levels of design. If you remember, in one of our first lectures, we were looking at the different levels. And this is the lowest level, in which we are looking at the workstation specification. So in terms of where are the machines for a specific employee and the materials that are needed. So designing for a workstation and then going into the next level in terms of designing the department, depending on how many workstations you're going to have. And then from there, bringing into the multiple departments and get to the larger picture. So the department specification, once we know the different workstations that we need to have inside the department, once the space requirements for individual workstations have been determined, the space requirement for each department can be established. So if you are going to have departments by product, then you need to understand what are the different workstations that are needed for each product. And combining those workstations will give you the size or the space needed to build that department. If you're just going to have a process department, like the ones that we have mentioned before, in which you have a group of parallel manufacturing lines, all of them performing the same type of operation. So you will need to know how many lines you're going to have, and then those are going to be the stations or the workstations for that department. And based on the number of lanes or lines, you will have the size of the department. So again, you go from the bottom up, look at the specifications of each workstation, and then build on top of that for departments, and then from departments to the facility. So the responsibility of the facilities planner is specifying what systems are required and where, integrating those systems into the overall facility. So the facilities planner must be aware that the cost of constructing, operating, and maintaining a facility is significantly impacted by the facility systems. So if we think about in Texas, the cooling system, so those are the type of system that we are referring to. So if you don't design properly for the cooling system, we don't take into account like the heat that could happen over the summer, and then the changing in temperature towards the winter season, that temperatures will be very cold. So keeping in mind the different and the uncertainty in terms of weather changes will affect your cost of construction and the operating at the same time. After you have built the system, if you didn't plan for enough, let's say shade, or you didn't plan for the proper insulation for the building, operating the facility can become very expensive. So the cost of constructing, operating, and maintaining a facility is determined by the facility systems. Critical factor affecting a facility flexibility is the facility system. So for example, if you set up a specific, let's say, again, HVAC system in location of the facility, and you're occupying a room, that room is going to be fixed for the long term. So that space is going to basically block some of the flexibility that you can have in terms of moving things around and so on. So a facility plan is not complete until all systems are specified. Facility systems have an important impact on employee performance, morale, and safety. So I cannot stress this enough. If you don't have a good design for your employees, for example, a design that has proper lighting or proper signs, they don't have a space for have lunch or a space for parking, all those things can impact your employee morale. And that can also impact the level of output that you will get from the facility. So it's very important. So a good design will take into account the safety and also the needs of the employees. And facility systems have an important impact on the fire protection, maintenance, and security of a facility. So if an emergency happens, are you able to, do you have a facility that will help you constrain those emergencies, and so on. So the facility system considered in this lecture are the following. We're going to look at structural system, atmospheric systems, enclosure system, lighting, and electrical systems, and life safety systems. Today, we're going to focus on the first two. And then on the next lecture, we're going to continue. So let's move forward. Structural system performance. So here's some information about the spacing between columns. So if you talk to anybody in civil engineering, they will give you a lecture on why columns are designed in a specific way, depending on how much weight they're going to handle and so on. From our perspective, we want also to have a design that will allow us to have some flexibility in terms of how to set up our departments, our workstations inside the facility. So having a column in the middle will create a problem in terms of flow from our perspective. So we have to find that trade-off balance in terms of the design based on the needs of the building from a structural perspective, and also design in terms of the needs for the operations of the facility. So the most common structural type for industrial facilities are the steel skeleton frame or reinforced concrete skeleton frame. If you have visited like any of these big warehouse, like Sam's Club or any other type of warehouse club, or for a sale, anything, you'll see those steel frame, steel skeleton frames most of the time. You don't see a lot of columns in between. So those are pretty common. Column configuration will impact the layout, as I mentioned already. So if you have a lot of columns in the middle, you know that if you have to design multiple manufacturing lines, that could create an issue in terms of your configuration. And the layout at the same time will affect the structural design. So one of the things that happened in this building, I think it was on the third floor where we have the big conference room. There's a column there that I believe was redesigned because it was kind of in the middle of that area in front of the conference room. So some things needed to be reconfigured. See on that third floor, is that where, or second floor? The second floor is where the large conference room is. So they made, at the end, they decided to make like a balcony from there, so you can see from the second floor to the first floor. But that was not the initial design. And it's because they needed to have some type of, they wanted that area to have a different feeling in terms of being welcoming. So the layout, what we want as a, let's say as a customer or as a design of the process or the operations, will impact the column configuration, and the column configuration at the same time will impact our layout. So the facilities planner must insist that the structural grid spacing optimize the function of the facility. So for example, in a warehouse, the column spaces or spacing should be dictated by the rack dimension and the access aisles between racks. You don't want to have too many columns that will avoid the pass, for example, of the forklifts that you will need to be moving around through your facility. Design for requirement. Common error in designing warehousing facilities is using building cost criteria to define column spacing and determine the grid configuration. So if you're basing those decisions in terms of cost, then you might not end up with the most efficient design. So again, it's a matter of having the right trade-off. The type of columns, we have heavy wall round or square tubular columns should be used in warehouses. These are a little bit more expensive than the H-beams, but provide a much better facility in the long run. They eliminate rodent and vermin nesting places, ensure easy maintenance and cleanliness, and provide the ability to place downspouts within the columns, and minimize the effect of denting on column strength, eliminate the corners that can pull packages from pallets when forklift trucks operators move too close to the column. So I don't know if you have seen those looks like this from the top. These are the columns that we are referring to. They have this shape. So those are commonly seen. Those are the ones that will create this problem. So recommendation is to have heavy wall round or square tubular columns instead of the H shape. Now in terms of, so that was in terms of the structural aspect or structural systems. Now we want to transition into the discussion of the enclosure systems. So the enclosure system provides a barrier against the effects of extreme cold or heat, lateral forces like the wind, water, and undesirable entries. That could be humans, insects, any type of pest that can put a problem into your facility. They can create a problem in your facility. The enclosure elements are floor, walls, and the roof. All three elements are intended to provide the facility with a specified comfort level and often impacted by the thermal performance of the building enclosure. So the following generalization holds true. The building enclosure plus the service input is going to be equal to comfort. So planning for this is important, and we are going to be looking at the impact of this cold and heat and lateral forces and so on in our design. So in terms of thermal performance, it's usually required to rectify the heat transmission imbalance between inside and outside areas of the enclosure. So if it is too hot outside, we don't want that to affect the inside of the facility. So you want to provide some type of cooling system. If it is too cold outside, then you are planning for a heating system. So we try to find that threshold by providing those that comfort threshold by providing those additional systems. So climate is the major determinant. One of the major problems in thermal performance, therefore, is how to make effective use of the solar gain. You see this building, you compare against MIDI, you'll see a lot of windows. Not only on the side of the building, but also in the hallways, you'll see a lot of glass. It's trying to get some of that solar gain inside the facility. So it's a good way to make use of what we have outside. But at the same time, that can create trouble during the winter season, because if cold enters the building, then we have to use more capacity to keep the temperature under or over a certain threshold. Solar transmission is effectively controlled, can significantly reduce the building dependence on artificial atmospheric systems. So here we have some design strategies. Here we have different ways in which the solar or the incident solar rays are impacting some different type of walls. So we have at the top a single glaze clear that has 90% of the incident solar rays are transmitted due to the poor absorption and reflection qualities of this single glaze element. So you see the arrow here representing the input and how much is transmitted into the inside of the facility. That's for single glaze. A double pane configuration with a heat absorbing element reduces the amount of transmission from 90 to 45%. So basically adding that additional heat absorbing piece. So this is called a double pane configuration. Only 45% will go into the facility. And then solar gain can be reduced additionally from 90% to 25% if a reflective glass member is substituted for a heat absorbing member in the double pane configuration. So in here, we will have this reflective piece. So there's some research going on also in terms of using, in additional to these wall protecting elements, the different paint. So there's some research, if I remember correctly, it was in Arizona, the University of Arizona. They are looking at colors of the paint in order to make it reflective. And they came up with a white color that will, if you paint the building with that specific paint, with that color, it can create a very high reflective of the solar gain. It's a reflective material of the solar rays, and it can help you reduce the heat inside the facility by just painting with that formula that they are creating. So again, a lot of research. This is becoming very important for many companies, saving money, looking at renewable sources of energy, at the same time looking at ways of reducing the amount of or the capacity of the system that they will need to keep their buildings within certain thresholds of temperatures. So barrier performance, the material selected, metal, plastic, should be more impervious to penetration. Thermal performance coupled with water exclusion forms the backbone of most of enclosure systems. So we want to keep humidity outside, especially if we are dealing with these sensitive products, electronics, and so on. So keeping water outside, humidity outside is very important. So there are two areas of consideration, the above the ground and below the ground. Above the ground, facilities planner must be aware of the problems that poorly designed roof can cause. So the primary performance of the roof is the water exclusion. Vapor migration, good insulation, and water barrier removal are essential to an effective roof system. So keeping the water outside, very important. I think we have some issues also with one of the storms in here at the university, in which we had some water coming into some of the labs. So that was better planning was needed to avoid those. An alternative is the green roof, and this is something that is becoming more popular. You have something like this, which these large areas are being used to have vegetation. So you have areas that are green and they're creating this additional barrier for water. So you have the vegetation, the growing medium, the filter membrane, waterproof repellent layer, support panel, thermal insulation, vapor control layer, and structural support. So all these layers keeping the humidity and water outside the facility. So what are the advantages? You reduce heating and cooling requirements and protecting roof components from UV rays, dealing with wind and temperature fluctuations and reducing the site's impervious surface area, thus allowing more parking or a larger building for the same site. So what we are saying here is you have to keep, every time you design a building, you have to keep some area for green, meaning vegetation, and for water dispersion. So if you have those located in the top of the building, the roof, then you will have more space outside, so you can build a larger facility. This is also good in terms of for the employees. So if you give them access to this area, it's like having a small park in the facility. So they can enjoy also the vegetation and the green space. Ground and below ground, this is another important aspect. So the foundation for your building. The ground and below ground condition for industrial facility is a concrete slab sitting directly on the ground. And the primary concern with ground conditions are water penetration and vapor migration. So here's an example of that concrete slab. So you have those areas being wired with this metal, and that provides some space, make it in a way that if you have movement within the facility, it's not going to break. So in addition to that, you have avoiding water penetration and also the vapor migration. So floor performance, in terms of most manufacturing and warehousing facilities, the floor is the second only to the roof in performance requirements. Over time, concrete slab floors tend to crack, dust, and generally deteriorate. some tips for preventing some of these conditions are as follows. Steel fiber, you can mix into the concrete, will not prevent cracks, but will reduce the width of the cracks once they occur. And synthetic fibers that can be mixed into the concrete to reduce segregation of the concrete mixtures as it dries, and therefore help to reduce the formation of these shrinkage cracks. So I think you have, doesn't mean that if you get a crack, it's going to be bad. What you want is those cracks not to be wider than certain range. That's where the problem starts. So these options right here are basically trying to avoid that when those happen, they don't become wider. So if they become really wide, then that means that you have a problem with your foundation and you will have to go and try to fix that. Okay, so now in terms of the last piece that we're going to study today are the atmospheric systems. And in here, we're going to be paying attention to the heating and cooling strategies for your facility. So the atmospheric systems provide the health and comfort of occupants and for the needs of the building equipment and machinery. Maintaining the work environment, codes require only minimum indoor temperatures in winter. So based on the codes for your state or for the area that you're working on or the country that you'll be working for, you have to follow that minimum required. So your system should be able to provide that level of comfort. And market standards for different building types provide more precise responses involving cooling and humidification. One example of such standards is found in healthcare facilities where humidity is held close to 50%. So that is because that will inhibit these bacteria or any other viruses to propagate. A more significant problem is the introduction of inorganic chemical pollutants into the building atmosphere from sources in the building. So the major air quality problem in most buildings is the buildup of odor and airborne particulate matter, and the rate of dilution is expressed in terms of fits to the cube, minimum minutes feet square of floor area. One can see that the way to eliminate unwanted substances is to dilute them by both by mixing stale air that is in the building and by adding fresh other outdoor air. So some buildings will have this type of system in which they would bring outside air into the facility and would extract some of the air inside the facility. So that's because they want to eliminate those unwanted substances from the facility. I have seen those systems also in homes. They will every half an hour or every hour, they will start up automatically, will pull some air from outside and will leave some of the air inside the house. This air exchange or dilution rate is typically expressed in 8 air changes per hour and is stipulated by local code requirements as it pertains to the building use. So here we have a table that shows the typical air change rate for several building use types. So for a residence, we have per area. So for toilet rooms and kitchen, exhaust air, this is the amount and the exchange, air changes an hour. For other rooms, we have natural ventilation for 5% of the floor area. Office commercial, it has other requirements. For school, you see that start increasing. For public assembly, goes higher, more people. Hospitals, 2. Labs, 1.2. And that's for the supply. and here's for the exhaust. So for an animal laboratory, you'll see that that is pretty high when compared to the other examples. So again, these are typical air exchange or change rate for several building use types. The equipment to bring in the fresh air and remove the stale air is primarily consideration in planning a facility. Equipment rooms, this space requirement is governed by the size of the equipment room. So for example, here, how much area for equipment room use should be allocated for your facility design. It will depend on the type of use. So if you look at the office or industrial facilities, about 5 to 7%. Public assembly, 10 to 15. For laboratory, you see that 25 to 50%, and for animal laboratory, it's going to be about 50%. So as the air change rate increases, the handling equipment area also increases. So 50% of your space is a lot. So keeping those requirements in mind, making sure that you have enough space for the rest of the facility and that you have the equipment that is needed to satisfy these requirements. Duct sizes can be estimated from air quantities and air speeds in ducts. So for the main duct, about 1,800 feet per minute. Branch ducts from 900 to 1,100 feet per minute. So for the lower sizes, these areas are also estimated from air quantities and air speeds. So for the exhaust, recommended airspeed about 2,000 feet per minute. For the intake, 1,000 feet per minute. A lot of information. I know this is very relevant for manufacturing facility, clean rooms. So we have a clean room here in the English, well, it's part of the English School of Engineering in RFM. So these are areas that are designed to be extra clean. So our control environments. So if you work for a facility, there's some special considerations for designing this type of environment. So facilities planners are often called upon to design carefully controlled environments for electronics, pharmaceuticals, and food processing operations. These control environments are known as the clean rooms. And one widely recognized method used to achieve these air quality levels is by the use of HEPA, or high efficiency particulate air filters. So this is the Texas State University MIDI clean room. These filters are used in a wide variety of industrial, commercial, and institutional installations where the highest possible degree of air cleaning is required. Again, electronics, pharmaceuticals, you want to eliminate any source of contamination, because that can impact the performance of your product. So by the use of these high efficiency filters, there's a way for us to keep those outside. Now, in terms of atmospheric systems, now we're going to focus on designing for the HVAC system. The purpose of feeding, ventilation, and air conditioning is to control the temperature, humidity, and cleanliness of the environment within the facility. The input required by an expert to design an HVAC system includes the facility layout and the construction specifications. So the facilities planner should be able to provide the HVAC expert with this input. So the type of information that we need to know in terms of designing this facility is the capacity that will be needed for this HVAC system. So understand how the HVAC expert translate this input into HVAC requirements. It's also part of our job. So these are the heating requirements for a facility. Is referred to a heat loss and is calculated using this formula. Okay, so if we want to know what will be the heating requirement for a specific facility, we have to look at different elements, and they are listed here. So that heating requirement or heat loss has look at the component, the heat loss through the floor, the heat loss through the roof, the heat loss through glass windows, the heat loss through the doors, the heat loss through the walls, and the heat loss due to infiltration. So for each one of these pieces, we're going to compute a value, and each of the individual heat losses will be calculated using this formula, where Q is the heat loss for the facility component, A is the area of the facility component, U is the coefficient of transmission of a facility component, meaning that this has to be given and is provided by the location of the facility. So there will be codes associated with this value. We have the temperature inside the facility and the temperature outside the facility. And then for air conditioning, we have a similar strategy. We can compute the requirement for a facility is referred as the cooling load, and that's obtained from this formula. The total cooling load involves the cooling load due to the floor, the roof, the glass windows, the doors, the walls, due to ventilation, due to solar radiation, due to lighting, and also due to the personnel inside the facility. So the cooling loads for the floor, the roof, the glass windows, the doors, the walls, and the ventilation are determined in the same way, just using the same formula that we were using for heating. But the cooling load for solar radiation is computed using this formula, in which we're going to multiply the area of the glass surface times the heat absorption of the building surface times the shade factor for various type of shading. Also, for the lighting, so the QL, we will look at the type of lighting that is used in the facility. So if it is incandescent, we're going to be using this formula. If it is fluorescent, we're going to be using this formula. And then once we get each piece of this, we can add them all, and that will be the cooling load for the facility. And then finally, for computing QP, the cooling load due to the personnel, we'll have this standard. So it would depend on if it is a man or a woman and the type of work that is being performed. So the cooling load from personnel may be calculated by determining the QP number of men and women performing light and heavy work and multiplying that times the heat gain factor given in the table. So the heat gain factor will be depending again in the type of work that is performed and also on the gender. So let's work on this example. Let's do some math using this information. So in this first example, we have an 18 feet tall facility having the dimension 250 by 100 feet and has 4 feet by 8 feet double pane glass windows and 2 3 by 8 doors or glass doors. on both the front and the back side. So it has 8 4x8 double pane glass windows and 2 3x8 glass doors on both the front and the back sides. The facility is made of 8 inches solid cylinder or cinder block and 1 inch metal insulated roof with an insulated ceiling and an uninsulated slab floor. Facility is located in Chicago, Illinois, so we want to know what is the heat loss. So this information, location, is important because these parameters are going to be based on the location of the facility. So those are by code. So we're gonna bring those, and there's those are tabulated as part of the code for the specific state. We also know TI and TO. So in this case, we're assuming that the temperature inside will be 70 degrees and the outside temperature will be 0 degrees. Okay, so we're going to start by looking at the expression. Let me change this color. So we are going to compute the QH, or the heat loss. So we have QF, which is for the floor, QR for the roof, QG for the glass windows, QD for the doors, plus QW for the windows, for the walls, plus QI for infiltration. So we have to compute each one of them individually and then add them together. And we know Q is going to be equal to A times U times TI minus T0 or T out. Where A is the area of the facility component, U is the coefficient of transmission, TI is the temperature inside the facility, and TO is the temperature outside the facility. Okay, so knowing all this, we're gonna go and compute the Q value for each one of these components. So we're gonna start with the floor. So QF for the floor we need to know the area of the floor. So this is a 18 feet tall with these dimensions. So the area of the floor will be 250 times 100. So we have a facility like this. 250, and then 100. And then it's 18 feet tall. So the area of the floor would be that area, 250 times 100. So 250 feet times 100. The U for the floor is 0.81. And TI minus T0, or T inside minus T outside, is 70 degrees minus 0 degrees. So for temperature, this is going to cancel out. For the area, this is going to cancel out the units. So the units for this is going to be U. U is this coefficient of transmission. Okay. So I'm doing the multiplication in order to keep the computations clean. I'm not including the units next to each of the numbers. But what I want you to see is that these units will cancel out because we have the temperature for the temperature difference, and we have the area, so feet squared will cancel out. So this will be 14.175 to 10 to the 5 BTUs an hour. Next one is QR. So the area of the roof will be the same area as the floor. So it's 250 times 100. This is the U parameter for the roof, and the temperature difference is also 70 minus 0. So this is 3.5 times 10 to the 5 BTUs an hour. For G is for the glass windows. So QG, for the glass windows, we know that we have 8 4x8 double pane glass windows. But those are for both the front and the back sides. So we have 8 in the front, we have 8 on the back. So total of 16 windows, glass windows. So we have 16. The area of the windows is 4x8. The coefficient is 0.63. And the temperature difference is 70 minus 0. So this is 0.226 10 to the 5 BTUs an hour. Okay, so this is for glass window. Glass window. Okay, so next one is for D. We start for the doors. Same thing. For the doors, we have two 3x8 glass doors. So two in the front and two on the back. So QD equals 4 times the size of the doors is 3x8. And the coefficient is 1.13. 70 minus 0 degrees. So this is 0. Oops, sorry. 0.076 times 10 to the 5 BTUs an hour. Next, we have W for the walls. So we have two sizes for the walls. And we will only consider the area occupied by the walls. So we know that in two of those walls, we have windows and doors. So we will have to subtract that area from the area of the walls. So this will involve some some additional computations here. So let's first look at the dimensions of the walls. So we have two walls that are 250 by 18. And we have two walls that are 100 by 80. Right, so that's what you're going to see now. So two walls, the area for the is going to be 18 times 100, so it's 1800 feet square plus 250 times 18. Times 4500. And then we have to subtract the areas of the windows and the doors. So it's 16 windows with an area of 32 feet square minus 4 doors with an area of 24 feet square. So all this multiplied by, so all this multiplied by 0.39. Oops. Times the difference, 70 degrees minus 0 degrees. And this is equal to 3.274 times 10 to the 5 BTUs an hour. Then we have QI. Will use the area of the roof. Can get some infiltration through the roof, and then some infiltration also through the walls. So we had to include all that area. So the area of the roof is 25,000 feet square. And then the area of all the walls, it will be 18 by 100 times 2 plus 250 times 80 times 2. That would be 12,600 feet square. All that multiplied by 0.20 times the temperature difference. And this is equal to 5.26 times 10 to the 5 BTUs an hour. Okay, so now we have the value for each one of those coefficients, heat loss for each one of them. Now, in order to get the heat loss for the building, we have to add them all. So QH is going to be summation of 14.175 plus 3.5 plus 0.226 plus 0.076 . Five point 26, 10 to the 5, and that's going to be equal to 26.51, 10 to the 5 BTUs hour. Okay, so that's for the heating system. On the next slide, we have an example for the cooling system. And we were still designing for Chicago. So for the same facility, given the following additional information, what is the cooling load? The front of the facility faces west, and all windows and doors have awnings. The lighting within the facility consists of 575 fluorescent luminaries, each containing two 60-watt lamps. Within the facility, 75 men performing light work and 50 women performing light work will be employed. The outside design temperature is 97 degrees Fahrenheit, and the inside temperature is 78 degrees Fahrenheit. Okay, so now we have those additional components: solar radiation, lighting, and personnel. So QC be equal to QF or QG plus QB or plus QW plus, these are new, QS for solar radiation plus QL for lightning and QP for personnel. Plus QB for ventilation. Okay, so we have the same formulas. QS equals A times, and we have some new formulas for solar, where A equals the area of glass surface H is the heat absorption of the building surface, and S is the shade factor. And we also have the QL that is going to depend on the type of lining that you have, and QP that is going to depend on the number of people and gender and the number of people that you're going to have in the facility. So we can compute the first 5 in the same way. We have QF the area is not going to change, the floor times 0.81. The only difference now is the temperatures. So the temperature outside is 97, and the temperature inside is going to be 78. That's the desired temperature for the facility. So this is going to be equal to 3.85 times 10 to the 5th BTUs in hour. For the roof, we have the same area, 25,000 feet square times 0.2, and the only difference will be that temperature difference. So now we have the outside first and the inside subtracted from the outside temperature, and this is 0.95 BTUs an hour. QG for the glass windows, we have 16. Are 32 feet square area, and the factor is 0.63 times 97 Fahrenheit minus 78 Fahrenheit. This is 0.06 10 to the 5 BTUs an hour. For the doors, same thing, QD, 4 doors, area of 24 feet square times 1.13 times the temperature difference. And this is going to be equal to 0.02 times 10 to the 5th BTUs an hour. And then QW, this is for the walls. So we have 2 walls that are this size and 2 walls that are this size. And we need to subtract the areas of the windows and the doors. 16 times 32 feet square minus 4 times 24 feet square. All this multiplied by the coefficient 0.39 times 97 Fahrenheit minus 78 Fahrenheit. So this is equal to 0.88 10 to the 5 BTUs an hour. Okay, so we did the first 5. Let's do solar radiation. Let's do the rest. So for QS, we need some additional information. So the heat absorption factor for the west side of the facility in Chicago is 100 BTU hours per feet square. And for the east side, is 75 BTUs an hour feet square. So these are parameters again by code. So we are providing that information that's coming from the guidelines for the design. So the shade factor also, the shade factor awnings are 0.3. So QS, look at the walls, I'm sorry, the doors and the windows that are located on the west side and the doors and the windows that are located on the east side. Okay, so we have 8 windows located on one side with an area of 32 feet square, plus 2 doors that have an area of 24 feet square. All that multiplied by the absorption factor for the west side, so it'll be 100 times the shading factor on is 0.3. And then we look at the east side, the same thing. We have the same number of doors in this case and same number of windows, so 32 feet square plus 2. This part was the west. Yes. And the 75 times 0.3 in this QS will be equal to 0.16 times 10 to the 5 BTUs an hour. So I'm going to stop here. We're going to complete this problem on Monday. You can try to finish up the problem by yourself if you want to, but we will complete this on Monday. There's an assignment was posted today. So if you want to start working on that, it's related to the material that we just covered. And that one will be due on Wednesday next week. If you are here to pick up your exam, you can come to the podium now and I'll give you the exam. If not, then I'll see you next week.